Hello everyone. Let's start solving the year 2021 organic questions of the JAM. Right. So we'll start with question number 1. Please remember I am solving only the organic questions. I will be solving 5 questions this time of the organic of 2021 JAM question paper. Right. So the first question says the major product formed for the following reaction. So what we are seeing is there is a molecule which looks quite bulky, and what we are adding is CF3COH, trifluoroacetic acid. It's a not very weak acid, but it's a still weak acid. It's a stronger than acetic acid, and important thing is you are hydrolyzing in presence of organic acid in water, and temperature is 0 degrees Celsius. That means very mild reaction conditions. If you look at this molecule basically is having 3 carbonyl groups, one aldehyde, one ketone and one more aldehyde. You are protecting with acetal protection. So you know what is acetal. So if you add an alcohol, if you add 2 molecules of alcohol on a carbonyl group, they both go and attack. So see here what has happened. You have added 2 molecules of CH3OH, methanol in it. So it has gone OCH3, OCH3. 2 of them are added, and so it is forming acyclic acetal like that. Okay. Similarly, here what has happened here, let us see. Here it is forming cyclic acetal. So they have taken methane, ethane diol. So you have taken ethane diol, ethane diol, which is protecting, ethane diol which is going and protecting here, and here they have taken propane 1,3 propane 1,3 thiol, dithiol. Okay, so it is like this, like that, SH and SH, right? So these are all ways of protecting aldehyde or ketone. So now very clearly what they have given you, they are seeing that you are deprotecting. They want to know that you understand about the deprotection or not, and about the reaction conditions for deprotection. So thing is, here we are adding very mild conditions. You are carrying out the reaction at 0 degrees Celsius and you are using weak acid. So one thing is, this will definitely not get deprotected, because for protecting cyclic thiacetal you need Hg2 plus. Without that it does not get out. Hg2 plus has strong affinity for sulfur, and that's how it interacts and allows it to leave. So this will not be removed, first thing. Now between this and this, acyclic acetals are much more labile for hydrolysis than cyclic. For this, generally, you know, if cyclic acetal is there, if you want to deprotect, you will need something like HCl and water and temperature, at least room temperature. But in 0 degrees Celsius and with trifluoroacetic acid, the fastest one, the easiest one to go will be this acyclic acetal. So when you do this, this part will get deprotected and rest will remain same. So the answer should be, the answer should be this one, A. So answer should be A. Let us see. Please go through it. Everything I said is written here. You can pause, read it, then keep moving. Right. So option A is the right answer. Moving on to question B. The major product formed for the following reaction. So two things we have to see. We are adding HCN and KCN, and temperature is very high, 160 degrees Celsius. What are we seeing here? We are seeing here is, it is alpha beta unsaturated ketone. So you are having this ketone group onto alpha, and beta you are having a double bond. So alpha beta unsaturated ketone. Now you know I must have shown all this, right? On position number 2 and position number 4, we have this positive polarity. So nucleophile Cn minus here can attack either position 2 or position 4. Why at position 2? Because carbon is attached here with oxygen. That too through pi bond. Pi bonds are loosely held, so it gets swayed away easily. So oxygen is electronegative. It pulls the electron towards itself, and therefore oxygen has more electrons, negative polarity. Carbon has little less electrons, so it has positive polarity. Another way is, you can see the resonance here. So this is one of the canonical structures, and it will be minor contributor, but certain extent it does contribute, and therefore there is a positive polarity on position number 4. So position number 2 is called as position number 2 is called as hard electrophilic center. Here the carbon, here the p orbitals on which attack will happen, its lobes are small because it has to oxygen electronegative. It takes the electron strongly towards itself, so the whole orbital shrinks. So only a hard electrophile will attack here. A hard nucleophile will attack here. Hard means, you understand, hard means hard to polarize. Soft means easy to polarize. So if the lobe is big, it is easy to polarize, easy to distort it. But if lobe is small, you cannot pull much, no, you cannot distort it much. So it is hard. So if any nucleophile is there who has a very small lobe, so you cannot polarize it much. So that will rather go on this position rather than a soft electrophilic center. Position number 4 is soft. Why? Because here carbon-carbon double bond is there. So this p orbital is quite large. Okay, this p orbital is quite large, and because this p orbital is quite large, it is easy to polarize. So soft nucleophile will attack position number 4, hard will attack here. What is the nucleophile here? Here the nucleophile is Cn minus. Okay, so now Cn minus negative charge is on carbon. Now you know carbon is not at all electronegative. Because it is not electronegative, it will not hold electrons strongly to itself. So the lobe is very large. Because lobe is very large, it is soft, and therefore it will attack at the position number 4. You get like that, and then negative charge comes here, takes here, and you get this C, right? And you get this product 1 for addition. Another way to look at it, see the temperature which it is being carried out. Temperature is 160 degrees, very high temperature. So when temperature is very high, you have to understand, even if reaction undergoes by kinetics, it has the chances that it will come back and give you thermodynamically more stable product. Attack and position number 4 is thermodynamically more favored, whereas attack at position 2 is kinetically favored. Okay. So why is attack at carbon number 2 kinetically favored? Kinetic means how fast reaction is happening. You understand, carbon number 2 has much more positive polarity than carbon number 4, right? Because here oxygen is directly attached to carbon, a lot of positive polarity is there, and therefore nucleophile, if it is in hurry, it will go and attack here. But if such a high temperature is there, it is in no hurry. Question number 4 is thermodynamically favored. Why? Because once the attack happens, question number 4, what is happening? You can see carbon-carbon double bond is lost, but C double bond O bond is retained. It is thermodynamically more favored to lose this C double bond C rather than C double bond O. C double bond O is more stable than C double bond C. Okay, so once this is found, more energy released. Here bonds are shorter. So this is stronger bond. To break it, you need more energy. So here, if you break it, is less stable. So imagine you are breaking a more strong bond and leaving a weaker bond here. So that is not thermodynamically favored. Whereas if you break this, you are leaving a stronger bond intact, and the weaker bond you are breaking it. Fine, and therefore the reaction happens here. I would have written all this here. See, loss of more stable C double bond O bond, whereas weaker C double bond C bond remains intact. The more stable C double bond O bond remains intact, and weaker C double bond C breaks to form new sigma bond, right? So the answer is option number C. Where is option number C? Let us look into it. The option number C is this, where we got 1 for addition, Michael addition. Right. Next question says, the compound shows proton NMR peaks at delta values in ppm. So it is not showing multiplets. You see, it is just saying the values, number of protons. 7.312 protons, 7.212 protons, 4.52 protons, and 2.33 protons. The structure of compounds is, these are the 4 structures which is given. So it's pretty easy question. So let's start with analyzing the spectrum. So first it says in the region 7, we know in the region 7 aromatic protons are there. So what are there in aromatic region? We are having around 2 kinds of protons. One is at 7.31 2 protons, that means 2 protons are there in aromatic region which are chemically in identical environment. Similarly, at 7.21 another set of 2 protons are there in aromatic region which are in completely identical environment, right? So basically on aromatic ring 4 protons are there. Let us look here. Here on A there are 5 protons, so this can be happily neglected, whereas possibility is still there between B, C and D. Let's look at next. Next it says 4.25 2 protons. So 2 protons mostly it looks like CH2 to me, and 4.5 is very high value, okay, unless very strong electron withdrawing groups are there beside carbon, such high thing will not come. So to me it looks like no, possibly beside the aromatic ring it is there and next to it is another electronegative group. So let us look here. So B has that kind of thing, CH2 is there beside the aromatic and electronegative. Here also C also has that CH2 beside that aromatic ring and then next electronegative atom. But what happens here? Here there is aromatic ring which will dechill to a little extent but not much, and here there is methyl group. Methyl will pump rather electrons. So I find D cannot be the answer because this is much more shielded. It should be highly deshielded to get the value of 2.5. You understand what is deshielded? That means electron withdrawing groups are there. When electron withdrawing groups are there, the proton comes at higher value. So B and C looks good to me till now. Let's look at other. And it says 2.33 protons, so mostly methyl besides CH2 or something like that. Okay, may not be CH2, but yeah, basically methyl, and that also is not so, it is not around 1. So it is not some simple CH2 CH3 kind of thing, sorry. So it has to be little bit deshielded, not much, but 2.3 is good enough. So Me on the benzene ring looks good to me, Me on the benzene ring. So now the competition is between B and C. The thing is, the only difference is we should have 4 protons forming 2 sets each, right? Let us look. If we have para disubstituted compound, and remember it is X and Y, not X and X. Now this hydrogen and this hydrogen is identical. Why? Because if I go one step I find X here, I go one step I find X here. If I come down H, I come down H, and then I come down here again I find carbon which is attached to Y. Similarly, these 2 hydrogens are identical. So very clearly this should be the answer because here 2 protons have identical chemical environment. Similarly, here also 2 hydrogens are in chemically identical environment. Whereas what happens when they are ortho-substituted? This is when para disubstituted is there. When ortho-disubstituted is there, A is different, B is different. Why? Because A, if I go to next carbon, I am seeing a carbon with X. In B, when I am going here, I am seeing a carbon next to that which is having Y. X and Y are different. So these 2 are 2 different. Similarly, C and D is also different. So it should have shown 4 different kind of protons, not 2 sets. So the answer has to be B, right? So whatever I have said is written here. Let us, you can read it slow, you can pause it and then read it. Right. So this is the answer. Moving on to the next question. The major product formed in the following reaction. So you are having a triene system. 3 alkenes are there together and you are putting temperature. So it is under thermal conditions. So mostly it is pericyclic reaction. So in pericyclic reaction it looks like electrocyclic rearrangement. Okay. So in electrocyclic reaction we have to understand the reaction conditions. So for 4n system H nu is dis. You have to just remember one of them, that you can do for others. So 4n H nu dis. So 4n thermal is con. And because 4n H nu is dis, so 4n plus 2 H nu is con. That means 4n plus 2 thermal is dis. Okay. So you look at this system. Look at this system. You can look it as this can go here and this can come here, and this part is left out, is what A and C are suggesting. But this looks tough, but we have to look and dis and con to get it. But mostly it look to us looks like, because three alkenes, the three double bonds are conjugated to each other, you have to consider the whole system. And the whole system, how many electrons are there? 1, 2, 3, 4, 5, 6. 6, that means is following 4n plus 2 rule. I hope you understand. N is the whole number. So here n is equal to 1. So 4 into 1 is 4 plus 2 6. So 4n plus 2 in thermal condition. So 4n plus 2 in thermal condition is disrotation. Now what is disrotation? See, in con rotation, the two p orbitals which are interacting to form the bond, they both move in one direction. That means both the p orbitals will move either in clockwise direction, or both of them will move in anti-clockwise direction. Whereas in disrotation, one of the p orbital will move in clockwise, the other will move in anti-clockwise direction. So let us look here. So this reaction is pretty simple. 3 pi bonds interact and you get 1 sigma bond, and 2 pi bonds rearranges. So this comes here, this goes here, and this comes here. So the bond, sigma bond, is found between this and this. Okay. So we have to look at the p orbitals here, and when they interact, so now we said it is disrotation. So one of the p orbital will rotate in clockwise, another will rotate in anti-clockwise direction. So now this is the one, because see here what they have given here in the question is, let us look at this. I will explain to you 1 second. Okay, so there is a double bond here. So when the double bond is there, you have to understand trigonal, and the shape will be trigonal planar. So one hydrogen is here, another hydrogen is here. So you can see, okay, so you can see that these two H are in E position, and this you see bulky group and bulky group, this is E. Similarly here also this is here, and so H will be up. So because this is trigonal planar, this is again H is here. So this is E alkene, this is also E alkene. Okay. So this is the geometry which you have to understand, and then we have to work on it. So now these two are there. So this p orbital, imagine this whole thing is on the screen, on which you are seeing. So that means this p orbital has to be perpendicular. That's how is sp2 hybridization. Okay. That means one of the lobe is coming outside the screen, another lobe is going inside the screen. Similarly, one of the lobe is coming outside the screen, another lobe is going inside the screen. So now it says disrotation. That means see this, I am rotating this one this direction. So this is clockwise. Clock, you see, clock moves like this. And so this one has to move anti-clockwise. You understand this lobe, which positive sign which I have shown, these both are coming outside the screen. Okay. It is coming exactly in front of you, perpendicular to this board, this screen. And therefore, when you are rotating like this, what happens? This is rotating. So this CS3 and H is there. So CS3 is going up, H is going down. Whereas when you are putting this down here, what is happening? CS3, sorry, I wrote by mistake CS2, it is CS3. So this CS3 is coming up and this H is going down. Please don't move ahead if you don't understand. This is very simple. Think about it, understand, then only move ahead. Okay. So you are rotating like that. So you understand this hydrogen is there and CS3 is there. So when you are rotating it like that, CS3 is coming outside the board, H is going inside the board. That's what I have written here. CS3 is coming outside the board, H is going inside the board. Similarly here also, when you are moving like that, then again CS3 is coming front and H is going back. So the answer is option number B. The answer is option number, is it? Yeah, answer is option number B. Both the CS3 are towards the viewer. It could have been shown both the CH3 away from the viewer also. That would have been perfectly fine. It has just been flipped. Wait, so fine. That's the last question for today's lecture. It says the major product formed in the following reaction sequence. See, they make quite complicated question. So you are having on pyridine carboxyaldehyde is there at meta position, right? And then you are first reacting with this looks like OMS, yeah, diethyl malonate, and then second you are reacting with dimethyl amine, then reducing with LiLH4. Finally, you are adding HCHO in presence of BF3. So it looks like they are going for acetal protection. Let's watch. Right. So first one is what is called as nicotine aldehyde. If you don't know, it's fine. So pyridine at meta position you are having CHO, and you are reacting with diethyl malonate. So now understand there is oxygen double bond O, and these two hydrogens which I have shown in blue, they are called as active hydrogens. They are acidic to a certain extent. Why? Because if you remove this proton, you get a negative charge, and that negative charge is getting stabilized this side. Also, it will get stabilized this side, right? It will get stabilized this side, two sides by resonance. So that means even after losing proton, the species formed is stable. That means it doesn't mind losing much this proton, because anyway after losing it is stable. Therefore, this proton is acidic. Acidic means easy to lose H+. So what happens? It undergoes condensation reaction. This is called as Nove-Nagel condensation reaction. So this forms and you get like this. I think I have shown mechanism. Yes. So in the reaction, first you make one of the tautomers. So you know ketone has tautomerization of enol, double enol. I hope you understand what I am saying. So this proton, if you imagine, if you put it something like this, okay, and you put it here. So what is happening is this bond, sigma bond, is coming, forming double bond here, and oxygen is picking up this proton. You get enol. So this enol is there, it comes back, and this goes and attacks. You get OH. And second step again, this forms enol, and this comes in, and you can get it here, and it picks up. This goes out as OH minus. In the meanwhile, it picks up this proton. So what goes out is minus H2O, and you are getting this species. Fine. Next is addition of dimethylamine. Now dimethylamine, you understand, you are having nitrogen. Now nitrogen has lone pair of electron. Nitrogen is not as electronegative as oxygen. Its lobe is quite big. So rather than attacking carbonyl group of the ester, no, it will attack this C double bond C bond, because this is soft center. This one would have been much harder center as we talked previously. So here also it will attack on the soft center, so that it undergoes kind of 1,4 addition. So this goes and attacks here, this comes up here, and this goes down and takes away proton from here, and you get addition of this amine. Next, what happens? Next, you are reducing with LiLH4. So only reducing species you can see here is ester. Ester, it will reduce to alcohol. It will reduce esters to alcohol, and you are getting OH here, OH here. Fine. Final step is you are adding formaldehyde. You are adding formaldehyde in presence of BF3. Okay. BF3 is Lewis acid. BF3 is Lewis acid. So it helps in formation of acetal. So because this diol is there, it will form cyclic acetal, right? So I think I would have written the mechanism. Yes, this goes and attacks here, and you are getting this species. Then oxygen goes and attacks here. This comes up, and this picks up proton. You get this. This goes and attacks here. You must practice all this mechanism, and then you are getting this acetal formation. So the answer is option number B. So that's it for today. Thank you very much.